I think I mentioned this in the workshop. I don't know whether everybody was at the workshop, but one of the things that we ran into is that modeling toolkit is just too slow for 100,000 neurons, let's say. And so Mason Protter has been working on this, on GraphDynamics for a little while, more than a year, right? Like how long have you been?
Yeah, about a year and a half.
A year and a half. And he essentially created his own compiler, right, to compile dynamical systems. And he will tell us all about it.
Okay. So yeah, we've already kind of heard about Neuroblox a couple times, so I'll skip over that. And basically, one of the core building blocks of our Neuroblox software for neurodynamic simulations is we're originally using a lot of modeling toolkit. So basically, what we do in Neuroblox is we build these structures that represent different building blocks of the brain. So it might be a neuron model, it might be a neural mass model, whatever. And it has information about parameters, states, equations, callbacks, stuff like that might happen during the execution of the model. And then we store these things, we generate a graph of all these different objects representing how they interact and talk to each other, and then we pass these things into, we compose them all together with modeling toolkit, defining connection equations that say like, okay, so the junction variable of this LIF neuron is the sum of all the voltages of the neurons that it's connected to. And then what modeling toolkit does for us is it performs structural simplification, eliminating all these junction equations and replacing, say, this JCN with the sum of all these voltages in. And so this modeling toolkit is a very high performance system. It works very well for small systems, which is what it was designed for. So like, for instance, if I had two integrated fire neurons and I just wire them together like this, have them each talking to each other, modeling toolkit will generate a kernel tailor-made for this problem, for these equations. And don't worry about what this says, but we basically just have a big list of equations describing how the dynamics of this system evolve. However, if we start cranking up these numbers and say 10 integrated fire neurons coupled all to all, we end up with order 100 equations in here. And this is because modeling toolkit basically is just a very general system, and it's designed thinking you're going to have heterogeneous structure, and we just have to simplify it down as much as we can and then write out those equations and pass them to Julia. So we get n-squared expressions here, but also Julia has an optimizing compiler. And optimizing compilers look for opportunities to fix things and make them faster. So it has to look at each pair of expressions. And so in general, you get n squared on top of that n squared. So you get n to the 4 in terms of the compilation effort you get with this. And every time you change anything, like the number of connections, the number of neurons, you have to recompile. So in practice, for a unrealistically dense system, so all-to-all coupled LAF neurons, we see something like n to the 4 scaling asymptotically once we get out to what I would call big systems for modeling toolkit, but in terms of neurobiology, very, very small. Like this is 160 neurons here, takes almost 2,000 seconds for a kind of end-to-end system where we compose all the blocks together, generate the system, do structural simplification, compile the system, and then solve it. So, that's what's being timed here, and it just starts exploding. We don't generally, now this wasn't such a big problem for us at Neuroblox, at least initially, because we don't generally care about these sorts of densely connected, soupy systems where you just have like lots of neurons talking to each other. We more care about these sort of structured models, like, for instance, this cortical striatal model that has been developed by some people in our lab, where you have kind of a very sparse cortex talking to a lot of control systems and stuff like this. But even this model, which is relatively big, it's but rather sparse, so it has 600 neurons and 6,000 connections. We start really running into some limitations that make us at least not want to make it bigger. So, for instance, the warm-up of this learning circuit is around 7,500 seconds, And if we want to do all these Hebbian learning trials where we show it an image and then it tries to categorize it, and then we give it some simulated apple juice to tell it was good or bad if it got the answer right, that took around 40 hours. And a lot of that time was actually in compilation time due to the parameter changing around weights in the model. So these long compile times, I mean, kind of obvious. It slows down how long it takes us to develop models. If I make a typo somewhere in a thing and then I have to wait 7,500 seconds just for it to compile and run and then give me garbage output, that sucks. And it also just limits the sort of models we can study. So to that end, we've been developing GraphDynamics. This is open source, and it's basically our modular framework for talking about clusters of interacting kind of enclosed systems that can send signals to each other and receive signals from each other. So instead of all the machinery of modeling toolkit where it might be trying to perform simplifications throughout a system, we know what variables need to be eliminated, and that's just these junction variables connecting neurons. But this is very general infrastructure. We think like this could be applicable for things like even PDEs or climate models or whatever, but we're applying it to neurobiology. And basically the key insight here is that we try and loop over repeated substructures and only do this sort of unrolling at the type level when you encounter systems that have different equations. So very roughly what this looks like is, say we have some system that has S and T type subsystems in it. We'll partition it by the type, so we take all the S type subsystems, put them into one bucket, so you know if you reach into this bucket, you're always going to get an S, and the compiler can make plans based on that, and all the T's go in their own bucket. And then we build up these connection matrices, which we also, okay, the formatting got screwed up, but basically these are sparse matrices describing the connections between each of these components. So, so we partition these based on the type of the connections. So in this thing, I've got the blue connection 1s, the orange connection 2s, and the green connection 3s. 3 sets of these partition connection matrices. And basically, so if you want to see S3 get a signal from S1, you would look somewhere in this connection matrix. If you want S5 to talk to T2, then you would look in this connection matrix, stuff like that. So we store this highly nested structure that tells us how all these systems are interacting with each other. And then basically the way we actually solve the differential equations is we unroll all these type level operations. So what that means is basically we tell it, okay, generate a loop, a dynamic loop over all the S's, where you say, okay, look at S1, and then for each of these outer matrix structures, then go into the innermost connection matrix and generate all the connections within the S's that go into S1. Feed that input to S1, go into all the connections from the S1s to the T2s, feed that in. And so on. And then we loop down here with a dynamic loop that doesn't scale at compile time, and then we do the same for the T's. And basically, we always are able to preserve type stability here at the cost of introducing some nesting. And basically, the advantage of this is that the amount of time you spend compiling is just eliminated. It doesn't matter if you're doing a 2x2 system or a 10,000 by 10,000 system. The compile time's the same. You're just talking about the runtime. So this is the same data I showed you before with that n to the 4 scaling, but I've put it on a log scale because otherwise you wouldn't be able to see this line, which is the time it takes GraphDynamics to do the same system. So this is the end-to-end comparison. And that cortical striatal example I talked about, that construction warm-up time went down to 75 seconds. It's a factor of 100 improvement and a factor of 10 improvement in the total learning structure. So that goes from waiting a couple work days to get some results to put something on in the morning and you can look at the result in the afternoon. And then it turns out that this green line here, this is also actually, there's a lot of overhead here, is mainly coming in the asymptotic case. That overhead is coming from walking through this graph of unstructured systems or potentially unstructured systems where it doesn't know what's in the graph, and then generating these type partitioned lists. And so if you have like a very homogeneous system, like say this big cluster of LAF neurons, you can actually provide your data to GraphDynamics in a pre-partitioned form, where you have all the connection matrices and the subsystems pre-partitioned, and then you can eliminate another couple orders of magnitude in overhead. So this lets us scale up to, I think I went to 40,000 by 40,000 densely connected LAF neurons, and I didn't go any further because my laptop ran out of RAM, just storing all the connection matrices. So depending on time, I'll give you a quick overview of how you can actually use GraphDynamics in practice. So basically, you would start off by just defining some sort of struct that holds data about that we'll use to basically represent like the initial state of your system before it gets passed into GraphDynamics. So in this case, I'm going to take some LAF neuron. It needs a name. This is basically used for the symbolic indexing, so we can generate plots and stuff at the end. And then it stores a bunch of parameters of the system. You then pass this to the GraphDynamics.toSubsystem function, which we overload. So we basically add a method to toSubsystem. And what we do here is we generate two objects, the subsystem states, and this tells GraphDynamics that basically the V and the G variables are going to be dynamical states that have differential equations describing them. And then all these other things, C, EM, RM, blah, 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 these are all parameters of the system. And and then we kind of wire those together into a subsystem of states and parameters. And the reason for that is basically that differential equations.jl expects the states to be in their own vector of just like a dense vector that it can do linear algebra on and stuff. So we need to be able to quickly separate out and the states from the parameters and stick them back together. Then after that, there's this subsystem differential equation. So you have to tell GraphDynamics what an input to a subsystem looks like. So this LAF neuron, for instance, just has a simple input that's so the initialized accumulator of this input is basically just to say like, okay, if there's no connections, then it's just gonna receive JCN equals 0. And I put this as a name tuple so that we can kind of keep track of the names of these different variables. So then the subsystem differential function, we then add a method to that where it takes in a subsystem, an LAF subsystem, an input. So that input will be of this form, but the actual value might change, and the time. And then we just unpack whatever variables we want out of it. So in this case, we took out the states, the parameters, and the JCN variable, and we calculate the differential equation like this. And we return a subsystem states object that has the same structure as the original states. But in this case, each variable is going to be the derivatives of the variables. So we want to generate a subsystem states that has the derivative of V and the derivative of G. And then the only other, so there's a couple more steps. If we want more structure, we have to tell it how connections work. So you can make a connection struct. So for instance, this is a struct representing connections between neurons, and it just carries some weight associated with it. And then we tell it how this connection struct acts on two neurons. So there will be like a presynaptic neuron in this case and a postsynaptic neuron. And we just say that the junction voltage going from the presynaptic neuron to the postsynaptic neuron is just the weight times the voltage of the presynaptic neuron. And then we return this thing. And this return needs to be of the same structure as this, is the only kind of constraint there. Other than that, you can kind of do whatever you want. So then, last thing here before we run it, we want to define callback events, because LAF neurons, it's too simple a model to have dynamical resetting of the voltages. LAF works by defining a callback so that when the voltage of the subsystem exceeds some threshold, then we want to reset the voltage back to some resting potential. So we can do that by telling GraphDynamics that LAF neurons have continuous events. We also support discrete events, and depending on the subsystem, it might make sense to use one or the other. Basically, the difference is that a discrete event, there's a condition that's checked at each time step, and then it just sees, is this condition satisfied? If so, apply the event. A continuous event has some condition that has to be met at a point. And so if the solver basically takes a big step and it sees that the voltage has spiked up past V threshold, then it takes a step backwards, and it will backstep until do root finding until it finds exactly the point where the voltage is equal to the threshold, and then apply this continuous event, which basically we pass it here a few arguments, the integrator, a view into the states, and a view into the params, so that we can modify the params and the states in place, and the subsystem originally. This subsystem is usually just used as a handle for dispatch. So basically what I'm doing here is I'm setting the voltage equal to this parameter E sub m, and I'm setting this conductance G equal to G plus this synaptic conductance. And then after that, you're free to start assembling and using these subsystems. So the easiest way to do this without the pre-partitioning is to define a graph system. And then you can basically define a bunch of these LIF structs and then add connections between them. So this add connection G between the source and the destination neuron with some connection variable here. This neuron connection, I've just randomized them and done 50% random sparsity. Then you can pass this graph system G into ODE problem and solve that problem, and with a chosen differential equation.jl solver. And it will just go. So here's a messy GIF of what the solution to one of these systems might look like. So yeah, that's kind of all I've got to talk about on GraphDynamics today, but I'll just quickly say a few words about what we've got planned next. I obviously still kind of sparse on the documentation, need to do more of that. We'd really like to support delay differential equations because there's a lot of models in neurobiology that need them. We don't support it yet. Currently, we only support one event per subsystem, but this is something that we don't really need, but we might want to at some point add ways to say, okay, this thing actually has 2 events, so you got to check both of them. Often we're kind of computing various things and storing it in some parameter in the middle of a simulation, like for lateral inhibition and stuff in the cortical striatal loop. We sometimes need to calculate, okay, which matrizome is getting more input, and then shut off the other matrizome or something like that. But when you do this, you kind of lose the history of what that computed state was throughout the thing by just overwriting parameters. And so we want a system for calculating computed states that don't come from differential equations and storing them and getting the history of those computed states throughout the simulation. And we also want dynamical connections. So for instance, with NMDA receptors, there's real dynamics happening basically in the connection between a presynaptic and postsynaptic neuron. And we can support this currently in GraphDynamics by basically just adding an intermediate node between the presynaptic and postsynaptic block and then giving that thing dynamics. But it can be kind of annoying to go in and calculate. You got to add one connection from the presynaptic to the receptor, and then the receptor to the postsynaptic, and then often a backwards connection from the postsynaptic back to the connector. And so it'd be good to give at least this intermediate block access to both the presynaptic and postsynaptic states at the same time for these connectors. So that's kind of my roadmap for the near-ish future. And I'm happy to take some questions.
Wasn't there I thought there was going to be an adapter.
So I think
You have an adapter for it.
so I had a question about like the inputs and the outputs. So I think in your example you had this JCN,
Thank you.
which was input. So and then in the connection rule, if I understood it right, you could kind of add things to input that. So what are the outputs for that?
Yeah, so currently we don't actually put any restrictions on what can be outputs because we don't really need to. So in the connection rule, you're allowed to basically take any variables from the presynaptic neuron and send it into the input of the postsynaptic neuron. We just need the inputs to be of a fixed form because otherwise it'll be type unstable when we're looping over all these structures. But we need that fixed. But the outputs we don't. That doesn't need to be constrained, basically.
Okay.
All right.